Uh, Hi everyone. So we have a problem today. It's called Dungeon Game. It's a problem from LeetCode. So it was asked by a lot of companies like Google, Amazon, Uber, and yeah, all other companies. So I'll try to explain the problem in a simpler manner, and then we can look at the various approaches of solving it. So yeah, there are some demons that have captured a princess. She's imprisoned and locked in a dungeon. So a dungeon is simply a 2D grid, okay, of m cross in size. It has m cross in rooms. So the princess has been trapped in the bottom right corner of the dungeon. So for this example, she has been trapped in the cell where -5 is there. Okay. So yeah, as you can see, this is the princess. She has been captured by some demons. So to save the princess, we need a knight. So the knight has some health points, right? Okay. So obviously it should be a positive integer, right? Because if health is zero, then knight is dead, right? Obviously. So health has to be at least one at all or at all points, right? So health has to be at least one, otherwise he will die. Yeah. So the next thing is some of the rooms are guarded by demons. These have been represented by some negative numbers. So you can see -2, -3, -5, -10. So on entering the room, the knight will lose those many points of health. But again, there are some power-ups also for the knight. Say for example, if he enters this room, then his health points will increase with +3. So the knight can move only rightwards or bottom or to the bottom right. So we want to return the minimum initial health so that the knight can rescue the princess. Yeah. So here are some examples. So to begin with, initially the knight enters at the room -2. So I would want the initial health to be at least 3, right? As of now. So because if say it was 2 or something lesser, then 2 minus 2 would have been 0, which means, yeah, it is pointless, right? So at least I want 3 for this moment. And yeah, they're saying that the initial health should be 7 because if you have any lesser, then yeah, the knight is going to die. So I would like to discuss one approach. See, I have made a simple drawing. I would like to discuss some approaches to solve this problem. The initial first approach which came to my mind was maybe I can somehow brute force this problem. So what I can do is I can check whether if initial health, okay, so if initial health is 1, will it work or not? If it is 2 or not? If it is 2, well, then will it work or not? If it is 3, and so on. Like I can try 4, 5, 6. So for 6 also, it might not work. So yeah, if it is 7, then it will work right for this problem as you have given. So if it is 7, then it will work for 8 also, right? Obviously, 9, 10. So what I can think is we can, you know, somehow brute force our way for all health points. 0, 1, 2, 3, 4, 5, 6, 7, and so on. 8. So yeah, for 7 and higher values, this will obviously work, right? But for values below 7, this will not work. So the first pattern that I see is we can maybe binary search on this thing on the entire range. So we can binary search on the output range. Yeah. So this is one good way which I felt. And yeah, what you might want to see is you want to check every possible way. It doesn't like see. Say for example, I start with initial health 8. So I will try all possible ways from here, right? Basically, what I'm trying to do is you can use either DFS or BFS, doesn't matter, but you can try all sorts of ways and check right whether it's working or not, like whether you're able to reach without losing, without dying, right? So if at any point in any path, if health becomes less than or equal 0, then reject that path, obviously, right? So yeah, this is one good method I felt. But yeah, as you can see, initially my start value can be 1, right? Because obviously at least 1 health. But what should be the end value? Like that is like very high, right? So we can decide that based on constraints. So yeah, I hope you guys can try this method. It's it's easy actually. So I would like to discuss the optimal approach here. So let me just quickly discuss the optimal way. So as you can see, if I start from this initial 0, comma 0 cell, I have choice, right? Either I can move right or I can move down at every possible cell. Obviously, you can't go left or upwards, otherwise the problem would be so much more complex. So at every possible cell, you can either move right or down. So yeah, and obviously you not want to die at any cell. So the way I can think about this, rather than starting from the 0, comma 0, basically, so say first of all, since we have choices and eventually, like let me just explain this. Consider this as some 1, comma 1. So from 0, comma 0, I have multiple paths, right? This is like, I could have reached 0, comma 0 to, I could have reached 1, comma 1 from 0, comma 0. Like, I could have went right and went down, or I could have gone down and went right. So basically, for any two generic points, there can be multiple paths, right? And from there, so see, from 1, comma 1, obviously there would be one optimal way, right? So the way I can imagine is, since we have so many choices, this is easily a DP problem. Yeah. So that is that. So let me just quickly come over here. And yeah, so rather than thinking in a top-down way, if we could have actually thought of this in a bottom-up manner, this would be in a really easy way, really easy problem. So yeah, see, so say for example, I'm at minus 5. Just imagine currently I'm at minus 5. So what should be the minimum health which is coming either from here or here? Obviously, it should be 6, right? If I'm coming either from this side or this side, minimum health should be 6, right? Because see, here it is -5. So I would like to take the absolute value of this and then add one, right? Because see, otherwise, say for example, if I had a health of 5 over here, so 5 minus 5 would be in 0 and I would have died. So at least I should have a 1. So you can take the absolute value and then add a 1 to it if it were negative. So see, just imagine, so this was for negative, right? What if it was, say, positive? Instead of -5, just imagine it was, say, +3. Yeah. So if it was +3, right, then a +1 would have been sufficient at the top, right? Obviously. So if it is positive over here, it doesn't matter. Like as long as the knight is alive from the other cells, we should be fine, right? So this is one thing. So yeah, the same thing I have written over here. So yeah, if it is negative or maybe 0, then I have written the condition for it. Same. I have taken the absolute value and added a 1. Otherwise, a 1 would have sufficed, right? So that is one condition. So yeah, how much was the initial value? -5. Yeah, so now what I'll do is this will return a 6, right? To where from wherever it is coming. Now just imagine the cell. I'll change the color. Yeah. Now what this thing can say is okay, to go to the next cell, I should have a minimum 6, right? Just imagine if it was say some +3. So this is getting a 6 from here, and this is getting like, see, this is invalid, right, from this portion. So here I can return some -infinity. Now what you can do is, acha, so from one side, sorry, we can return, yeah, we can return +infinity, sorry. So from one side, I'm getting 6, and from the other, I'm getting +infinity. So I can say that, acha, so I shouldn't, see, obviously I'm trying to minimize the health points, right? So I should take 6, right, and not +infinity. So what I can do is I can take the minimum of the bottom and the right, and then I can take the difference with my current value, which should be the minimum for the above ones to reach the current cell. So yeah, this is what I have written over here. So for here, I'm getting 6, and I'm taking 6 minus 3, which is 3, right? So that I'll return to my higher value, saying that to come near me, you should have at least a value of 3. So yeah, that is that. So say for example, it was 3 over here. Then it would come over here and it would get a plus 3, right? So it would become plus 6. Then obviously it would be just sufficient enough to reach the princess. But let's just say, for example, that okay, maybe so it was plus 30 over here, right? Before I needed a 6 over here, but it's already 30, right? So it is really just like I already have a 6 and it doesn't really matter to me. What matters is that my above one or the left one, they should just have a at least plus 1. Basically, they should be just alive, right? So yeah, in short, indirectly we can say that if this result is less than 0, I would say that at least okay, I need a 1. Otherwise, I can just return this result directly. Yeah, obviously at 0 condition also. Or in other ways, we can write it in this way. So yeah, I'll just quickly show this code part. So yeah, I have written a basic recursion and then memoized it over here. So yeah, if result is greater than 0, then I can return it. Otherwise, if it is 0 or negative, I can just return a 1. And here I have handled the plus infinity part, right? Which was coming from here, like the out of bounds condition from this portion. So handle that condition before it. And here's the base case. Yeah, if dungeon of I is ij is greater than 0, then I can just simply return a 1. Otherwise, if it is negative, then I can just take the absolute value and add a plus 1 over it. So yeah, these are all some initializations. And yeah, I've just initialized with minus 1 the table. And yeah, I've taken 200 obviously because due to the constraints. So yeah, this was the memoization. To adjust for the top-down code, I have initialized the base condition, obviously, right? So what was the base condition? M minus 1 and j and n minus 1, right? So I have handled that part over here. I have initialized it. Same code only. And from m minus 1 to m minus 1 I and j equals n minus 1. Yeah, I have adjusted the bounds. And to explain this part again, you can just imagine the recursive tree, right? Yeah, as you guys can see, like you can just imagine somewhere at the bottom, we'll have a leaf nodes, right? So we obviously have to start from there. And yeah, so obviously I'm skipping the base condition. And here, see, I have taken my table size as m cross n. So the outer bounds part was there, right, over here. So rather than storing it in the table itself, what I've done is I have made a separate, like, initialization. Let's see if the new index which you're finding If they are inside a boundary or inside a grid, then it is fine. Otherwise, we can take the infinity part, and obviously it will get handled as a minimum function rate. So yeah, this was the bottom up, and obviously we can later space optimize it. I'll just show just a minute. Uh, yeah, so since as you can see, T of I and T of I plus one, right? So basically, what I need is I'm currently depending on my current row and my next row rate. So we can just optimize that part very easily. So instead of taking a 2D matrix, I have divided into a next and current rate. And yeah, wherever it is I plus one, you can replace that with next. And wherever it is just I, T of I, you can replace it with current. And at the last, just make sure to, initialize your next with current and return next of zero. So yeah, that was that. So yeah, this is all I wanted to discuss. So yeah, that's it, guys. Thank you so much for watching.